going to consider how to fill out the speeding up, slowing down lab, which looks like this. Prior to doing this, you should have followed Mr. De La Paz's videos and already had completed sections F of this problem. So, how do you fill out the rest? Well, we're going to go ahead and jump to problem number 2. So turn to page 2 in your packet. And notice that we're not trying to trick you here what's happening. For number 2, this thing is going to slow down while moving in the positive direction. It's also important that you read the directions. It says give the car an initial push up the ramp. So it's going to be moving at time 0. And then you're supposed to stop the car at the highest point. So when it gets somewhere up here-ish, it's going to slow to a stop and you're going to hold it in that position. Let's remind ourselves what that video looked like when Mr. De La Paz showed us on the YouTube video. The car slows to a stop and it stops at the highest point. And what do the videos look like? As that happened, take a look at how the shapes of our position versus time, velocity versus time, and acceleration versus time graph moved along as he went up there. And there's the shapes of ours.
Increase sales up to 21% by adding another sale.
And let's jump back to our graphs. So the shapes of the graphs that he had there looked like this and like this. And the acceleration versus time graph was a horizontal line below the time axis. Now, when filling out the other sections of this, section C says, is the direction of the velocity positive or negative? Well, we know that the slope of a position versus time graph is the velocity. And since this is a positive slope, we could say it's a positive velocity. Or we could look here and notice that these velocities are above the time axis instead of below, so that's going to be a positive velocity. Let's get back to section D and C later. Over here is section G. Down the road, we're going to list off these questions and say, please consider your ABCs, because they're all broken into section G point A, G point B, G point C. When considering the slope of this position versus time graph, is the slope increasing, decreasing, or constant? Well, taking a look at the slope, is it a straight line or a curve? Well, it's a curve, so is it increasing or decreasing? Please take a moment and jot down these notes before moving on. Increasing suggests that the slope is getting steeper, and that could look like this, or it could look like this. A decreasing slope would be one that's becoming less steep, and that could look like this, or it could look like this. The slope starts out steep, and as time goes on, the slope becomes more flat. Starts out steep and becomes flat. If a slope is constant, it means it's simply a straight line. Pause if necessary to jot down those notes. Back to station 2. So when looking at the slope of our position versus time graph, at time 0, we have a tangent line that is a big positive slope, suggesting we start with a big positive velocity. A little while later, the slope is less steep, but still positive, and finally the slope goes to 0. So that's a decreasing slope. Because the line is still tilted mostly upward, that's a positive slope. And we already know that the slope of any position versus time graph is the velocity. Now, what's so powerful about these ABCs is if we read the ABCs for our position versus time graph, it will tell us what the velocity versus time graph looks like. Look at the words. It says we have a decreasing positive velocity. And that suggests a smaller and smaller and smaller positive velocity. In fact, we start with a big positive velocity and we end with a velocity of 0. So that does show a decreasing positive velocity. Now, let's consider the slope of the velocity versus time graph. When looking at this slope, is it a curve or a line? Is it an increasing, decreasing, or constant slope? Because it's a straight line, we can say that it's constant. The slope of this graph is tilted downward, which tells us that the slope is negative. A zero slope would be one that is horizontal, positive, tilted up. So this is a negative slope, it's tilted downward. And what does the slope of any velocity versus time graph tell us? That's something we learned right before break. The slope of the velocity versus time graph tells us the rate at which velocity changes with respect to time, which could be speeding up or slowing down or changing direction, and we call that acceleration. Acceleration. And if we read those three in a row, that's a constant negative acceleration. Next up, we go down to our acceleration versus time graph. We see here that we have a horizontal line below the time axis. So because it's a straight line, that slope is constant. Because it's not tilted up or tilted down, tilted up would be positive, tilted down would be negative. It's a horizontal line, so that's a slope of 0. And we know that the slope of any graph tells us the rate at which the y-axis changes with respect to x. So this is the rate at which acceleration changes with respect to time. This is the first time we've considered what the slope of an acceleration versus time graph represents. And it shows how acceleration changes with respect to time, and we call that a jerk. If you can think about if you've ever been in a car that stopped quickly or on a bicycle that ran into a curb, you don't slow down very smoothly in those situations. It's a really aggressive way to slow down, in which case you actually might feel a jerk in the car or on the bicycle if that were to happen. Let's go back up here to letters C and D. D and B. We already answered C, that the velocity was positive. But what about the acceleration? Well, there's two graphs that you can look at to find out about the acceleration. The first thing you can do is you can look at the slope of your velocity versus time graph. And over here, we said we had a negative acceleration, which tells us the acceleration would be negative. So the acceleration is negative. The other way you could look at it is just by looking at the slope, or looking at the acceleration versus time graph. All positive accelerations would be above the time axis. All negative accelerations would be below the time axis. So again, this suggests a negative acceleration. So that's your answer for letter D. So the only part we haven't taken care of at this point is the motion maps. To do that, we have to consider the starting position and relative speed, as well as the direction the object's going. To find starting position, our best bet is to look at the y-intercept of a position versus time graph, which tells us our starting position, and that starting position happens to be 0. Next up, we want to consider our initial velocity. To find the initial velocity, we want to look at the y-intercept of a velocity versus time graph, which is the velocity at time 0. We also could look at that by reminding ourselves that we had a big positive slope at the beginning of our position versus time graph, so we had a big positive velocity, that's where we got that. So it's going really fast in a positive direction. So it's going to have a big change of position. I'm going to go ahead and count over here 5 dots. 1, 2, 3, 4, 5. And that will start with a big positive velocity. But as time goes on, remember it's slowing down while moving in a positive direction. So we're going to have smaller and smaller changes of position. If that's 5 dots, I'll go over 4 dots, and then 3 dots, and then 2 dots, and then 1 dot. As we have smaller changes of position, and as the velocity gets smaller and smaller and smaller and approaches 0, the velocity vectors that we're drawing on here are going to get shorter. So we're not going to put hash marks because none of these are going to be the same size. And that one's going to be really small. Now, that's as far as we asked kids to go in class today. However, they ask you to include acceleration vectors as well. And while the velocity kept having a smaller and smaller positive velocities, the acceleration was a constant negative acceleration. Now, we may not have done this any time prior to now, but an acceleration vector for these would be what's the rate of acceleration at each of these positions. Because the acceleration is negative, it's going to be pointed in a negative direction, which would look like this. But because it's a constant acceleration, they're all going to be exactly the same size. Now I'm going to go ahead and steal my infinite cloner button on this one. And so at each of these position dots, and we get an acceleration vector for this. But what about the last dot? That last black dot right here doesn't actually have a velocity vector. Right here, there's no velocity vector there. Why? Because it's stopped. At time 0, it was stopped. The velocity was 0, the slope of the position versus time graph is 0. It's not moving at the highest point. So does it get an acceleration vector? And the answer to that is yes. Why? Because we said that when an object is accelerating, its velocity is changing. Let's look at the final acceleration down here. Is the final acceleration 0 or that same constant acceleration it had? The other thing you can think of is what's happening the moment before it stopped. It was moving. Well, if it was moving and now it stopped, the velocity had to change, and by definition, we consider that an acceleration. So that last position dot still gets an acceleration vector, the same size as all the other ones, even though it's no longer moving. So, in review, you're going to be finishing up all parts of the speeding up, slowing down lab on all 6 stations. You'll need to fill out parts B, C, D, and G. You should have done F already by watching Mr. De La Paz's videos. In part G, you're filling out your ABCs. Describing the slope of the corresponding graphs as increasing, decreasing, or constant, positive, negative, or 0, and tell us what the slope of each of those graphs represent. After you fill out your ABCs, I'd come back up here later and then fill out part C, which direction is the velocity, D, which direction is the acceleration, and I would come back and do the motion maps last. I hope that helps.